Building a battery for a high-power electric go-kart. As some of you know, I am building a new large-scale electric go-kart. This vehicle is designed to have a high-output electric powertrain with custom-built geared hub motors. Inspired by Formula FSAE electric vehicles, but not bound by the same rules, this build stretches the cockpit to accommodate an additional passenger and adds otherwise banned features such as reverse, more lights, and a traction fan to help with not slipping the tires during acceleration. With this type of vehicle demanding bursts of more than 20 kilowatts, it needs a custom battery that can provide these ridiculous power levels and have enough capacity to run for at least half an hour. Thankfully, I have had a couple years of experience working on the battery and as powertrain lead of my university's Formula FSAE electric team. Because some of these cars use up to 80 kilowatts, they have to use extremely high voltage architecture, with my team's car using around 400 volts. This offers a lot of advantages in terms of needing less current and overall system efficiency, but it requires a rigorous amount of safety protocol, and every voltage-rated component is extremely expensive. Doing some research on available components, I found that the power system cost per kilowatt to be lowest using 72-volt components and running them closer to their maximum voltage rating, which in the case of the controllers I chose was about 90 volts. This was a pretty good compromise between voltage and current, which meant my system could be built around a current rating of 250 amps. Now, in designing a battery layout, you have a couple of things to consider depending on the type of cells used. Each cell has a voltage range from peak voltage at full charge to a minimum voltage that will be at a lower state of charge or under extreme load. The nominal voltage is typically in the middle of that range, where the battery will stay during the majority of the charging and discharging process. Each cell also has a charging and discharge current rating, typically with reference to the cell's capacity known as the C rating. After looking for adequate battery cells, I found some cylindrical lithium iron phosphate cells with a peak voltage of 3.65 volts. These cells also had a capacity of 15 amp hours and could handle a 5C discharge, which corresponds to a maximum current of about 75 amps that each cell can provide. Knowing this, I arranged the cells into parallel groups of 4 to provide burst currents up to 300 amps, and put 24 of these banks in series to make a peak voltage of 87.6 volts at full charge. A 24 series 4 parallel pack seemed like it would work well for my systems, so after a test batch, I ordered 96 more cells. 24 cells in series was also really convenient and allowed me to split up the pack into 4 22-volt modules for safer assembling and handling. Splitting the larger pack into modules is required by Formula student rules, and is based on both the voltage and stored energy contained within each module. The go-kart modules turned out to be 1.15 kilowatt-hours each, with a total pack capacity of 4.6 kilowatt-hours. Going on to design the module, a fairly common method for making Formula student modules is to use a 3D printed structure, as long as the glass transition temperature of the structural plastic is far enough above the maximum allowable battery temperature of 60 degrees Celsius. So I designed the printable module in a structure that is printed out of PETG plastic with an 85-degree glass transition, giving me a 25-degree margin at the overheat shutdown temperature. These modules were also air-cooled and had spaces between each cell for cooling air to be sucked through. When the cells arrived, I packed them into the module shells. I needed to figure out a way to attach the bus bars between the copper terminals. Thankfully, I was able to borrow a friend's spot welder, and after trying many different strip types, I found that a thin interface nickel strip with a much thicker current-carrying strip on top provided adequate adhesion and minimal bond resistance. After several weeks welding hundreds of strips and frequently overheating the spot welder, I had laid enough layers of nickel to take 250 amps continuously. Once the tedious spot welding process was complete, I placed 2 temperature sensors on the central and top module cells and ran cell tap wires to a plug that connected to the BMS. After quick charging verification for each module, I wrapped each one in insulation paper to insulate it from the steel box that it would be placed inside. Although the standard for Formula student tractive battery containers is aluminum, and I welded this year's and last year's battery box, I did not have a TIG welder, so I designed a simpler steel construction box that can be easily MIG welded. I welded the box together from sheet steel in tube sections, sealing up every gap except for the intake vents. With module side slots, air passages, a central electronics area, and mounts on each corner, my battery box came together smoothly, and it was given a coat of paint to prevent rusting. Thankfully, all the modules fit well, and I was able to crimp together a nice high current path with some thick orange wires. The BMS, isolation relay, manual service disconnect, and a fuse were mounted inside the box, and a large mixed-flow impeller fan was added to provide required cooling air. I put on an aluminum lid and powered up the BMS to check if things were connected properly and get the first batch of data. Because everything was looking good, I plugged it into charge, and after a couple hours it was up to about 70%. Then I got both gear hub motors and the respective controllers wired up and ready for a test. Two, one. With this entire out-of-car powertrain finally working, this car is getting even closer to completion, and a nearly complete chassis means the start of system integration will be the next step. Having just come back from racing at the Formula FSAE competition in Michigan, I'm even more inspired to get this build driving after seeing the wild variety of electric power systems and car designs. Stay tuned and subscribe for the next steps toward driving this vehicle.